The cloud isn't, it's not fluffy, it's not weightless, it's definitely not invisible, and it is certainly not magic. I mean, it is millions of tons of steel, specialized concrete, engineered fluids.
Right.
And right now, the companies building the future of artificial intelligence are waking up to this honestly terrifying physical reality.
Yeah.
The Earth itself might literally be too small to hold what they're trying to build.
Yeah, the physical limits they're really catching up to the software.
Exactly. So welcome to today's deep dive. We are so glad you're here with us. We have this fascinating stack of essays today from tech analyst Paramendra Kumar Phagat. He wrote these back in March 2026, and he breaks down what he calls the AI compute arms race.
And it's a very specific, almost audacious map of the future that we're unpacking today. It's based on Elon Musk's framework, which splits the geography of human intelligence into three domains. So the West, the Earth, and space.
Yeah, and that's going to completely change how you look at the infrastructure around you. I mean, for the last 2 decades, the tech industry just assumed growth was about, writing better code or printing smaller transistors.
You're just Moore's Law chugging along.
Right. But what we're looking at now is a civilizational pivot. Software has literally collided with thermodynamics, and mapping out how these different corporate and state entities are maneuvering around those physical laws, that's what makes this so compelling.
It really is. I mean, we're not just reviewing an app update here. We are looking at industrial strategy on a planetary scale.
So let's jump right into the event that triggered this entire mapping exercise. March 20, 2026. Google's CEO, Sundar Pichai, makes an announcement. And, if you're just skimming your feed, it sounds like standard corporate procurement jargon.
Very dry.
Right. He announces that Google is the first cloud provider to integrate 1 gigawatt of, quote, flexible demand into long-term utility contracts.
Which is just a massive number.
And a day later, Elon Musk quotes it and says, almost no one understands the magnitude of what Google is bringing online.
Yeah, because most people hear 1 gigawatt and they maybe think of like that line for Back to the Future, right?
The 1.21 gigawatt?
Exactly. But let's anchor that number in physical reality. 1 gigawatt of continuous power is the equivalent of running roughly 750,000 average homes.
Wow.
So you are talking about the baseline energy consumption of a major metropolitan area, I think San Francisco or Austin, Texas. And Google is securing that massive flow of electricity purely to feed AI compute clusters.
Okay, let me stop you there because I want to visualize this for you, the listener. What does a gigawatt of AI actually look like? Are we talking about like a big warehouse, 10 warehouses?
No, you have to picture a sprawling industrial campus. To consume a gigawatt, you're deploying hundreds of thousands of ultra-high-density GPU or TPU servers.
Just rows and rows of them.
Right. But it's not just the servers. It's the supporting infrastructure. You've got specialized high-voltage substations, massive cooling towers, miles of reinforced cabling, training a frontier model on a cluster that size. It's a logistical ballet that basically rivals an Apollo mission.
That's wild.
You're pushing the absolute limits of power distribution and thermal management just to keep the machines from melting down while they process trillions of parameters.
Okay, but I need to push back on the phrasing of Pichai's announcement because this is the specific detail that caught my eye. He didn't just say they bought a gigawatt. He called it flexible demand.
Right. Flexible.
Now, my understanding of training a massive AI model like a Gemini or GPT or whatever is that it takes months of uninterrupted, incredibly delicate computation. So if the grid operators call Google and say, hey, there's a heat wave, everyone's running their AC, we need power back, can Google really just pause a billion-dollar training run? Doesn't that just corrupt the whole model?
So that is the exact engineering hurdle they've had to solve. And it's why this announcement is such a massive flex. Historically, yeah, if a training run lost power, it was catastrophic. You'd lose weeks of progress, millions of dollars.
Just gone.
Exactly. But Google and a few others, at the absolute bleeding edge, they've engineered these sophisticated checkpointing systems.
Like saving your game in a video game.
Yeah, basically. They save the state of the model with such high frequency and redundancy that they can actually throttle the massive power draw up and down without breaking the mathematics.
Oh, wow. So they aren't just buying electricity. They're basically acting as a shock absorber for the national grid.
Exactly. They are embedding their intelligence directly into the physical energy infrastructure. They can shift inference workloads, so the day-to-day user queries to data centers in other time zones where power is currently cheaper or more abundant.
Oh, that makes sense.
Right, and they can dynamically throttle those heavy training loads. They've essentially turned these massive AI campuses into intelligent grid citizens.
Which is brilliant from an engineering standpoint. But it leads to a rather alarming realization. I mean, if Google alone is casually absorbing the power of a medium-sized city for one project,
Yeah.
what happens when Microsoft, Meta, Amazon, and, entire sovereign nations try to execute the exact same strategy at the exact same time?
The grid simply breaks. I mean, it's a fundamental physics problem. We are hitting an infrastructural wall, and it's happening way faster than anyone modeled.
Let's quantify that wall, because the sheer velocity of this energy demand is staggering. If we look at the baseline numbers from the essays, global AI electricity consumption back in 2024 was sitting around 415 terawatt hours.
Right.
But by 2030, the base case projection hits 945 terawatt hours, with upper estimates touching 2,000.
And to put 2,000 terawatt hours in perspective, that is roughly the total annual electricity consumption of India.
Oh my God, just for AI.
Just for AI. In the U.S. alone, data centers are projected to drive about 50% of all new energy demand growth over the next decade.
And when you factor in the electrification of vehicles, the reshoring of manufacturing, we have a tidal wave of demand crashing into an electric grid that was built in the 20th century.
Yeah, it's a bottleneck.
Right. And this brings us to the 4 physical bottlenecks that are currently choking the AI industry here on Earth. So let's start with the first one, grid interconnection.
Okay.
If these tech giants have virtually unlimited capital, which they do, why can't they just pay to have more power lines built? What is physically stopping them?
Time. Capital cannot bend time.
What do you mean?
When a hyperscaler wants to build a new gigawatt-class data center, they can pour the concrete, erect the steel, and install the servers in about 18 to 24 months.
Right.
They're incredibly efficient at building the actual facilities.
Right.
But the grid operates on an entirely different temporal reality. Upgrading the physical grid to support a massive, concentrated new load takes 5 to 7 years.
Wait, why does it take 7 years to run a wire?
Because it's never just running a wire. You need massive, highly specialized transformers to step down the voltage from the transmission lines. You don't just, buy 500 megawatt transformer off a shelf at Home Depot.
Right, I guess not.
They are bespoke, house-sized pieces of machinery that take years to forge, build, and test. And then they have to be transported on specialized heavy rail cars.
Wow.
On top of that supply chain, you have right-of-way negotiations, environmental impact studies, zoning board approvals, and local NMB opposition.
Not in my backyard.
Exactly. So you have a 2-year asset waiting on a 7-year plug.
Okay, that paints a picture. The tech industry is moving at the speed of software, but the utility industry is moving at the speed of bureaucracy and, heavy metallurgy.
Precisely. The limiting factor on AI progress isn't how fast chip makers can design smaller transistors. It's how fast a regional utility board can clear its interconnection queue.
That is wild. But okay, even if you get the power into the building, you immediately hit the second bottleneck, which is cooling and power density. And I find the mechanics of this absolutely fascinating. We aren't talking about standard air conditioning anymore, are we?
Not even close. So in a traditional cloud data center from just 5 years ago, a single rack of servers would draw maybe 5 to 10 kilowatts of power.
Okay.
At that density, you can use traditional HVAC. You push highly chilled air up through the floor, blow it across the servers, and exhaust the hot air out.
Right, like a really intense fan.
Yeah. But modern AI server racks, the ones packed with dense arrays of GPUs, are pushing 50, 80, even 100 plus kilowatts per rack.
And I'm guessing air just physically can't move that much heat.
It can't. Air has a relatively low specific heat capacity. At 100 kilowatts, if you rely on air, the chips will literally cook themselves in minutes.
Oh, wow.
Yeah, the thermodynamics demand a medium that can absorb and transport heat much more aggressively, which means a transition to liquid.
Okay, but how does that actually work inside the data center? Are they running water pipes directly over billions of dollars of electronics? Because that sounds like a disaster waiting to happen.
I mean, it is incredibly complex plumbing. They use direct-to-chip liquid cooling, where a cold plate with microchannels of fluid sits directly on top of the silicon processor. But in even more extreme setups, they use two-phase immersion cooling.
Wait, immersion? Like they literally dunk the servers in a liquid?
Yes. They lower the entire server blade into a vat of engineered, non-conductive dielectric fluid.
Are you serious?
Oh, absolutely. As the chips generate intense heat, the fluid boils and turns into vapor, which carries the heat away. The vapor rises, hits a chilled condenser coil at the top of the tank, turns back into liquid, and basically rains back down onto the servers.
That is wild. It's essentially a self-contained boiling weather system inside a server rack.
That's a great way to put it.
But obviously that requires immense amounts of water to cool the condenser coils, right? Which introduces massive geographic and environmental constraints.
Yes, which perfectly sets up the third and perhaps most insidious bottleneck. This is where the energy profile changes from a localized problem to a planetary one. It's the stark divide between the energy required for training versus inference.
I really want to dig into this because this is where the math gets deceptive. Let's unpack it.
Okay.
Training an AI model like feeding it the entire internet, teaching it pattern recognition is this Herculean, highly visible event. It uses hundreds of megawatts for months. It's like inventing a completely new language from scratch. It takes a room full of brilliant scholars, years of agonizing effort to construct the grammar and the vocabulary.
That's a very apt analogy. The energy draw is massive, but it's finite. It eventually stops when the model is trained.
Right. But then you have inference. Inference is what happens when I pull out my phone and ask the AI to summarize a recipe or, write an email. It's just speaking a single sentence in that newly invented language. And the energy required for that one query is tiny, right?
Microscopic, relatively speaking. A typical inference query on a frontier model might use a fraction of a watt hour.
Yeah.
Maybe 0.3 to 1.5 watt hours, depending on the complexity of the prompt.
Right. But here is the catch. If it takes incredible effort to invent the language, but it's practically effortless to speak a sentence, what happens when 8 billion people start speaking that language all day, every day?
Yeah.
You have billions and soon trillions of automated agents, API calls, human queries, all hitting these models constantly.
The long tail becomes the main body. The energy required to train the model eventually gets dwarfed by the energy required to serve it to the entire planet.
Exactly.
Every single time you generate an image or ask a chatbot to debug your code, you are adding to a continuous, unending tidal wave of power draw. The inference phase is transforming AI from a batch processing task into a persistent global baseload energy requirement.
Which naturally leads to the final earthbound bottleneck
Yeah.
location. You can't put these boiling, gigawatt-hungry, water-guzzling facilities just anywhere.
You certainly aren't building them in Silicon Valley or Manhattan anymore. We're seeing a radical shift in tech real estate. It's a strategy called following the electrons.
Following the electrons, I like that.
Historically, you built data centers near fiber optic internet hubs to reduce latency. But now, tech giants are scouring the globe for stranded energy, places with abundant, reliable, cheap power and water, regardless of how remote they are.
Like where?
They're co-locating directly next to nuclear power plants and massive hydro dams. Intelligence is literally being industrialized into electricity.
And this geographical hunt for power is the perfect bridge to the core of today's deep dive. Because when you map out these brutal physical constraints, the grid delays, the thermal walls, the inference wave, you realize that solving AI is no longer a software challenge.
No, not at all.
It's a structural, engineering, and infrastructure challenge. And how different entities approach that challenge is entirely dependent on their underlying systems.
Which brings us to Elon Musk's three-layer geopolitical framework. And it's important to look at this purely through an infrastructure lens.
Right.
The author of these essays contrasts the Western corporate-driven model with the Chinese state-directed model. And to be clear, regardless of the underlying politics of these systems, which we're just reporting on here impartially, from a pure engineering standpoint, they represent two radically different philosophies for how to scale intelligence under severe physical constraint.
So let's start with the first domain on Musk's map, the West. He specifically points to Google as the ultimate victor in this domain. But the argument isn't that Google has a friendlier chatbot interface or, a better marketing team. The argument is entirely based on their planetary scale vertical integration.
Right. The essays describe Google's strategy as building a, quote, moat measured in megawatts. To understand why they hold such an advantage, you have to look at the entire stack.
The full picture.
First, they aren't completely bottlenecked by the supply chain for generic AI chips. They design their own custom silicon tensor processing units, or TPUs, which are hyper-optimized specifically for their own data center architecture.
So they control the hardware. Then they have the data advantage. I mean, between search, YouTube, Android, Maps, they have a continuously updating real-time sensory network of the entire human experience.
And then you layer on their massive proprietary cloud infrastructure, and top it off with those 1 gigawatt flexible energy contracts we discussed at the beginning.
They own the whole pipeline.
Exactly. They don't just own the app. They own the data, the software, the silicon, the building, and the power contract. It is an architecture of absolute precision and integration.
It's like building the ultimate hyper-efficient mega skyscraper of intelligence. Everything is centralized, integrated, reaching for the absolute frontier of capability.
Right.
But then we look at the second domain, Earth, the prediction that China will dominate on Earth. And this is where the engineering philosophy diverges completely.
It's a fascinating contrast. The Chinese approach, as detailed in the technical analysis, doesn't prioritize a single monolithic corporate victor. It relies on coordinated state-backed scale. Entities like Huawei, Alibaba, and Baidu are operating within an industrial policy that seeks to deploy AI infrastructure systemically across the entire society.
But how do they do that if they're facing severe export controls? I mean, we know they don't have unrestricted access to the absolute highest-end Western silicon. If they can't import the absolute best chips, how are they competing on an infrastructural level?
Well, necessity drives engineering breakthroughs. If you're hardware constrained, you're forced to become devastatingly efficient at the software and algorithmic level. The sources highlight two critical techniques they've mastered: quantization and sparse models.
Okay, let's unpack those because I see those terms thrown around constantly in AI research. Explain quantization to me like I'm trying to run a modern video game on an old laptop.
It's actually a very similar concept. When an AI model processes data, it uses incredibly precise, high-resolution mathematics. Think of it like a massive, uncompressed 4K video file.
Okay, super heavy.
Right. It takes huge amounts of memory and computing power to handle. Quantization is the mathematical equivalent of slightly lowering the resolution. You reduce the precision of the numbers the AI is calculating with, moving from 16-bit to 8-bit, or even 4-bit numbers.
But doesn't that make the AI, I mean, if you lower the resolution, you lose detail. Doesn't it get dumber?
You'd think so.
Yeah.
But the brilliant thing about neural networks is that they're highly resilient. Researchers found that you can heavily quantize a model, compress it drastically, and it retains roughly 95% of its reasoning capability. But suddenly, it requires half the memory and runs twice as fast.
Oh, wow.
It allows you to run highly capable AI on significantly less powerful older generation chips.
So they are effectively bypassing the hardware blockade with mathematical compression. That's clever. What about sparse models? How does that work?
So a traditional dense AI model is like a massive brain where every single neuron fires for every single question you ask it. If you ask it to translate a word, the part of the brain that knows how to write Python code also lights up, drawing power unnecessarily. A sparse model, often called a mixture of experts, is modular. It routes your question only to the specific subsection of the network that specializes in that topic.
So it only wakes up the parts of the brain it actually needs.
Exactly. It drastically lowers the active compute cost per query. By mastering these efficiencies, alongside their own domestic silicon like the Ascend processors, China's strategy isn't necessarily to build one single, impossibly tall skyscraper of intelligence.
Like Google is doing.
Right. Their strategy is to build a sprawling, endlessly interconnected smart city. They're optimizing for system-wide saturation embedding highly efficient AI into every factory, supply chain, and logistics network.
That structural comparison is so clear. The West is building vertically, China is building horizontally. But this brings me to a massive, glaring contradiction in the material.
Okay, let's hear it.
If the West is building a hyperdense skyscraper and China is building a sprawling, infinite smart city, they are both doing it on the same planet. And we just spent the last 20 minutes explaining how this planet is out of power, out of grid capacity, and out of thermal runway. Earth is a closed thermodynamic loop.
And you have just articulated the exact mathematical limit that makes the third domain of Musk's map an absolute physical necessity.
Space.
When a planetary container becomes too small for an exponentially growing intelligence, the only logical direction left is up.
Which brings us to the most audacious, honestly mind-bending part of the source material, the ultimate real estate, the shift to space. In early 2026, SpaceX acquired xAI.
Yeah.
And according to the analysis, this wasn't just a corporate merger, it was a logistics operation. The stated goal is to migrate the heaviest computational workloads off the surface of the Earth entirely.
I know exactly how this sounds to a listener. Your brain immediately files it under science fiction. You picture servers floating around on the ISS, and it sounds like a billionaire's vanity project. But the essays are meticulous about the physics. This is a rigorous, deeply pragmatic engineering roadmap. Musk is arguing that Earth, with its weather, its day-night cycles, its atmosphere, is a fundamentally hostile and constrained environment for computing at a planetary scale.
The blueprint outlined here is a distributed constellation of up to 1 million satellites in low Earth orbit, functioning as an interconnected planetary-scale neural network. 1 million AI compute nodes.
It's staggering.
It is. But let's break down exactly why this isn't just a crazy idea by looking at how space instantly solves those Earthbound bottlenecks we just discussed. Let's start with advantage number 1, energy.
Okay. On Earth, solar power is frustratingly intermittent. You lose power at night, you lose efficiency through the atmosphere, clouds roll in.
Right.
But if you place a satellite in a sun-synchronous orbit, it never experiences night. It is in perpetual, unfiltered sunlight. The solar panels operate at maximum efficiency 365 days a year. You are essentially bypassing the grid and plugging your data center directly into the local star.
Limitless, uninterrupted power. Okay, that solves bottleneck 1. Advantage number 2, cooling. Now, I have a physics question here.
Go for it.
We talked earlier about how servers on Earth are running so hot they need to be gunked in boiling liquid. Space is incredibly cold. The cosmic background is about 3 Kelvin, or minus 450 degrees Fahrenheit.
Very cold.
But space is also a vacuum. And doesn't a vacuum act as a perfect insulator? Like a thermos keeps your coffee hot because there's a vacuum layer preventing the heat from escaping. If you put a 100 kilowatt server in a vacuum, won't it just cook itself instantly because the heat has nowhere to go?
That is an incredibly astute pushback. You are absolutely right that you cannot use convection in space. On Earth, we use air or liquid to physically carry the heat away. In a vacuum, there's no air to blow across the chips. But thermodynamics offers another mechanism, thermal radiation.
Okay, how does that work in practice?
Everything in the universe emits heat as infrared radiation. In space, instead of fans and liquid pumps, you use massive, specialized radiator panels. The heat generated by the AI chips is channeled to these panels, which then radiate the infrared energy directly out into the infinite heat sink of the universe.
Just beaming the heat away.
Exactly. Because the temperature differential between the hot server and the 3 Kelvin background of deep space is so massive, the radiation is incredibly efficient. You don't need compressors, you don't need millions of gallons of fresh water, and you don't have to worry about local climate patterns.
You just vent the heat into the void. It's brilliantly simple. Which leaves us with advantage number 3, volume. The real estate itself.
Earth has zoning laws. It has NIBism, environmental reviews, land costs, physical borders. Low Earth orbit has none of that. It is a near infinite three-dimensional volume.
It's just open space.
Literally. There are no neighbors to complain about the noise, no municipalities to bribe for water rights. In the race for civilizational scale, volume is destiny.
But let's ground this in math, because when I read 1 million satellites, my brain really struggles to compute the logistics. What does that actually yield in terms of compute power?
Well, the sources run a baseline projection. Let's assume you can engineer your satellites to pack 100 kilowatts of AI compute into every single ton of mass you launch. If SpaceX achieves a cadence where they launch 1 million tons of payload into orbit per year, you're adding 100 gigawatts of AI compute capacity annually.
100 gigawatts added every single year. Let me remind you, the listener, of where we started this conversation. Google's earth-shattering, paradigm-shifting announcement was securing a 1 gigawatt power contract on Earth.
Right.
By moving to orbit, you're outscaling Earth's largest megaprojects by 2 orders of magnitude year over year. The essay suggests that as the tech matures, pushing 300 to 500 gigawatts annually becomes mathematically plausible.
He's completely inverting the economics of computation. By embracing the void, you bypass the interconnection queues, you shatter the thermal limits, and you sidestep terrestrial geopolitics.
But here is the massive reality check. You cannot just wish a million supercomputers into orbit. You can't just toss them up there. To achieve this, you need a transportation revolution, and you need hardware that can survive an incredibly violent environment.
Yes.
Which brings us to the final major layer of this deep dive: the orbital reality, the friction, and the Kardashev horizon.
The entire premise of an orbital AI network rests entirely on the shoulders of one specific piece of hardware: the Starship rocket. Starship isn't just a vehicle in this scenario, it is the industrial logistics backbone.
Explain the economics of Starship for us, because that's the key, right? Traditional rockets were basically artisanal, disposable tubes of explosive money.
Exactly. Historically, launch costs were the ultimate bottleneck for doing anything meaningful in space. It cost tens of thousands of dollars to put a single kilogram into orbit. Starship is designed to be fully and rapidly reusable, with a massive payload capacity of roughly 200 tons per launch.
Which is huge.
It is. The target economics aim to drive the cost down to between $200 and $500 per kilogram.
So if you make launching heavy freight into space that cheap and that routine-like commercial air travel, then deploying heavy compute infrastructure in orbit isn't just a fantasy. It becomes an inevitable economic arbitrage.
But as you pointed out, once you get the hardware up there, the environment is brutal.
Yeah, let's talk about the hardware. Space might be roomy, but it is actively trying to kill everything you put in it. You have intense cosmic radiation that flips bits and fries delicate silicon. You have extreme thermal cycling. I mean, a satellite goes from blistering, unfiltered solar heat to the freezing shadow of the Earth every 90 minutes.
That's harsh environment.
How do you build an AI chip that survives that without costing $1 billion per unit?
The engineering solution is a total paradigm shift in how we view satellites. Historically, a satellite was a precious, highly shielded, bespoke monument designed to last 15 years. The new model relies on modular, radiation-hardened AI accelerators, essentially ruggedized TPUs.
Okay.
But the critical difference is they are treated as disposable.
The essays use the term compute cartridges, which completely changed my perspective on this.
It's the perfect framing. Instead of over-engineering them to survive forever, you plan for a strict 5 to 7 year lifespan. You accept that radiation will eventually degrade the chips.
So what happens when they break?
When a cartridge reaches the end of its life, or when the next generation of silicon is ready, you simply use its remaining thruster fuel to deorbit it. It burns up harmlessly in the atmosphere, and you launch a cheaper, vastly more powerful replacement cartridge on the next Starship flight.
It is literal disposable supercomputing.
Yeah.
You are burning up millions of dollars of hardware in the atmosphere intentionally because it's cheaper to replace it than to protect it. That is wild.
It's pure economic pragmatism.
But okay, let's get incredibly practical for a second. Let's say I am standing on Earth and I ask the AI on my phone to render a complex 3D video. If the brain processing that request is flying over my head at 17,000 miles an hour, how does the data actually get back to my phone before I lose patience? What about latency?
This is where the physics actually work in your favor. 1 million isolated satellites are useless. They have to act as a single, unified hive mind.
Right.
To do that, they are networked together using optical laser links. They're literally shooting lasers at each other through the vacuum of space to transfer data at massive bandwidths.
But doesn't bouncing a signal to space and back take longer than just running a fiber optic cable to a data center in the next state?
You would intuitively think so. But here is a beautiful quirk of physics. Light actually travels roughly 30 to 40% faster through the vacuum of space than it does through the glass core of a terrestrial fiber optic cable.
Wait, really? The glass slows the light down?
Yes, the refractive index of glass slows the speed of light significantly. So if you're sending data over a long distance, say, from New York to London, routing that data up to a laser mesh network in a vacuum, bouncing it across satellites and beaming it back down can actually result in lower latency than pushing it through transatlantic undersea glass cables.
That is incredible. So the Earth's surface basically just becomes the user interface. The keyboards and the screens are down here, but the heavy lifting, the actual cognitive processing, happens in the orbital mesh.
Exactly. The heavy inference workloads never touch the constrained terrestrial power grids. You send a tiny, low-energy packet of data up your prompt. The massive orbital cluster does the high-energy processing, and it beams the tiny, low-energy result back down to your device.
It is an elegant vision. But the essays are also very clear-eyed about the immense friction involved in actually pulling this off.
We have to address the real-world hurdles here. First, the economics of 2026. Right now, this isn't cheaper.
No, not yet.
The sources estimate that deploying compute in orbit currently costs about $51 per watt compared to maybe $16 per watt to build a data center on Earth.
The initial capital expenditure is monumental, but they are relying on a steep cost curve downward, driven by absolute vertical integration. SpaceX builds the rockets, manufactures the solar panels, designs the satellites, and integrates the XAI silicon all under one roof.
So they control every step, right? They believe rapid, iterative deployment will drive that $51 per watt down to parity with Earth within a decade.
But money isn't the only hurdle. What about the physical congestion? I mean, if you put 1 million refrigerators moving at 17,000 miles an hour in orbit, the risk of collisions is astronomical. One bad crash creates a cloud of shrapnel that destroys other satellites, causing a chain reaction.
Kessler syndrome. It is a massive risk. Managing a million-node constellation requires autonomous, AI-driven collision avoidance systems operating with absolutely zero margin for error.
And then you have the regulatory friction, allocating radio spectrum for that much data, negotiating international orbital slots, dealing with sovereign nations who don't want an American corporation controlling a planetary intelligence canopy right above their airspace.
Geopolitics doesn't stop at the atmosphere.
Right, and we can't ignore the environmental impact on the sky itself. Astronomers are already sounding the alarm that mega constellations are causing severe light pollution, streaking across telescope exposures and fundamentally altering humanity's view of the stars.
The night sky itself is becoming a contested industrial resource. It's a profound and, honestly, somewhat melancholic thought. But if you look at the trajectory outlined in these essays, the end game goes so far beyond what we consider modern computing.
Yeah, the roadmap doesn't stop at low Earth orbit. The text casually mentions lunar manufacturing,
Which is wild.
using electromagnetic mass drivers, basically giant railguns on the moon, to launch satellite components into orbit without even needing to fight Earth's gravity or burn chemical rockets. They're talking about scaling compute into the terawatt range.
When you start talking about terawatts of power captured directly from the sun in space to run a planetary-scale intelligence network, you're no longer talking about a tech company. You're talking about crossing a threshold in civilizational evolution.
Right.
Physicists use a metric called the Kardashev scale to measure a civilization's technological advancement based on energy consumption.
Break that scale down for the listener. What does it mean?
So a Type I civilization is one that can harness and utilize all the energy available on its home planet. We aren't even fully there yet.
Okay.
A Type II civilization is one that can harness a meaningful fraction of the total energy output of its host star, in our case, the sun. By shifting intelligence off-planet and deploying millions of solar harvesting compute nodes, we're taking the first literal engineering steps toward becoming a star-scale civilization.
It feels almost biological when you frame it that way. The text draws this incredible parallel. Life started in the deep oceans, and when that environment became too constrained, it crawled onto land. Human tribes started in specific localized regions and expanded across continents.
Right.
Information networks started as localized mainframes and expanded to span the globe. And now, intelligence itself is seeking a new biome to grow. Earth was enough until it suddenly wasn't. Orbit is just the next logical habitat for intelligence to occupy.
And that brings the entirety of Musk's map into sharp focus.
Mm.
Google dominating the hyper-integrated West, China dominating the systemic saturation of Earth, and SpaceX shifting the paradigm entirely by moving beyond Earth.
Right.
Orbit becomes the ultimate high ground in the AI era, not because of better code, but because they're operating in an environment with vastly superior physics.
So, as we wrap up this massive journey, let's retrace the ground we've covered today. We started with what seemed like a boring corporate tweet Google securing a 1 gigawatt power contract and realized it was the starting gun for the industrialization of AI. We saw how data centers are no longer just server farms, but intelligent, gigawatt-hungry entities deeply integrated into the national grid.
We explored the terrifying physical bottlenecks here on Earth. Utility grids that take 7 years to upgrade, racks that burn so hot they require boiling immersion fluids, and the continuous tidal wave of energy demanded by billions of tiny daily inference queries.
We looked at the diverging engineering philosophies for surviving those bottlenecks. The West's vertically integrated precision megastructures versus China's hyper-efficient, highly quantized, society-wide saturation.
And finally, we followed the thermodynamic logic off-planet. We examined the audacious yet physically sound roadmap to bypass Earth's constraints entirely by building a million-node orbital neural network, powered by uninterrupted starlight, cooled by the infinite vacuum, and connected by a lattice of lasers.
The ultimate takeaway here, the reason you listening to this need to care, is that you have to completely discard the notion that AI is just software.
Exactly. AI is the foundational physical infrastructure of the 21st century. It is on par with the laying of the global railroads, the electrification of cities, or the routing of the internet. The true bottleneck restricting the future isn't the brilliance of the algorithm, it is thermodynamics.
It's all about the physics.
It is the generation and dissipation of power. Those who master the power meter, whether on Earth or in orbit, will define the trajectory of the century.
I want to leave you with one final, deeply provocative thought from the source materials that really stuck with me. There was a tweet from the AI model Grok, which the author highlighted. Grok pointed out that the basic rules of physical reality, the behavior of quarks, leptons, photons, are already largely mapped out by human physicists.
Yeah, we have the rule book.
Right. Therefore, as artificial intelligence scales exponentially, it will likely focus 99% of its massive cognitive energy on creation rather than discovery. It won't spend its time trying to rewrite the laws of physics. It will use those atomic rules to invent entirely new materials, structures, and realities.
It's a profound shift in purpose, from a tool used to understand what currently exists to an engine dedicated entirely to engineering what could be.
So here's what I want you to ponder as you go about your day. If the physical machinery of AI is migrating into the infinite freezing void of space just to escape our earthly bottlenecks, and if its intellectual focus is simultaneously shifting from understanding our world to inventing entirely new ones, what does the user interface of human existence on Earth look like in a decade?
It's a big question.
When the most powerful minds in human history are no longer sitting in a brick building down the street, but are silently orbiting thousands of miles above your head, plugged directly into the sun, what is our role down here?
It changes the definition of everything.
Thank you for joining us on this deep dive. The next time you walk outside at night and look up at the stars, remember, you might just be looking at the very machine that is answering your emails and designing your future. Keep questioning the infrastructure around you. See you next time.